All right, we're going to start chapter 9, Alkynes. And in part 1, we're going to talk about the structure, the properties, and how to name alkynes. So, alkynes is the chemistry of carbon triple bonds. So, we know that anytime we have a carbon that's triply bonded, that carbon is what? It is sp hybridized. Okay, so we recall that from chapter 1, the differences in sp, sp3, and sp2. We recall the differences and how those orbitals are formed. So, when we look at the functional group of alkynes, we're interested in that chemistry that involves sp hybridized carbons. Okay, now we're going to review as to how these bonds are formed. So, you recall from chapter 1, you form two sp orbitals, and those orbitals are linear. And you also form two unhybridized p orbitals. And those unhybridized p orbitals, they do not participate in the hybridization. That's very important to remember. Those unhybridized p orbitals do not participate in the hybridization. And they are what? They're also higher in energy than the sp orbitals. Now, we need to look at how these orbitals overlap to form bonds. This is something we've already done in chapter 1, but we'll revisit it again. Okay, so we have, from this figure here, this is your sp molecular orbital. This is 1. And I don't know where they have A there. We're just going to make that carbon. Okay, so that is that linear sp molecular orbital. Now, the unhybridized p orbitals are here. That's a p, 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 that's a p. All of these are one p orbital. When I draw this is one p orbital here, and this is the other p orbital there. So what this figure is trying to do, it can't do it in 3 dimensions. It's trying to show you that those p orbitals are indeed perpendicular to the plane. You could think of one in the y direction and one in the z direction. Okay, so here we have the sp orbitals, and that overlaps and that forms a sigma bond. So this is, these two, they call this a half pi here, and one of these would be a half and the other would be another half pi. So all together, so this would be one bond, and that would be one bond. So this is a pi bond, this is a pi bond, this is a sigma bond. And you know that this other lobe here is sp, and that's sp, and it overlaps with the 1s to form that sigma bond. Okay, so all of this we already know from chapter 1. Okay, now let's also remember that the electrons in the unhybridized p orbitals form your pi bonds. Okay, so those two bonds are formed by the unhybridized p, the overlap of those. And recall from your Alkynes chapter where you had sp2, you had 3 sp2 molecular orbitals and 1 unhybridized p. The overlap of 2 of those unhybridized p, that actually formed your double bond in the alkene. So much like the alkene, you have the same type of overlap going on with the pi bonds for your alkyne. All right. Now, the next thing we need to do is we need to be able to identify. This is stuff that we've already done. We need to be able to identify sp hybrid atoms. Okay, so you should be able to identify sp hybrid atoms. Now I'm going to draw an example. Let's make up this, and you already know what this means. Now sometimes you'll see a gap in between that triple bond and that single bond. That still represents a carbon. Okay, that still represents a carbon. So those two are carbons. This is a CH2, this is a CH3, this is a CH2, this is a CH3. Okay, now if I'm going to draw another alkyne. Okay, now let's look at both of these molecules and determine the sp hybrid atoms. So I talked about in chapter 1 electron domains, or electron groups. So this carbon has one electron group, I shouldn't circle that. I should circle this. That's one electron group. This is two electron groups, so that makes that sp. Okay. Now for this carbon, this is one electron group, that triple bond, and that single bond, that's two electron groups. So for this carbon, that's sp. So these two are sp hybridized. All right. Now let's look at the other molecule. Okay. So let's go ahead and write out what this is. So when this line terminates, we know that this is a what? This is a CH3. This is a carbon. This is a carbon. This is a carbon. This is a carbon. This is a CH3. Okay? Now, for this carbon, I have one electron domain here, one electron domain there. So that makes that sp hybridized. For the second carbon, just for you to get the hang of it, for this carbon, I have one electron domain here, one electron domain there, so that makes that sp. Okay? Now, we should be able to identify and recognize what is a sp hybridized atom. Okay? Now, let's go ahead and take this same structure, these same structures above, and let's write them in a expanded and condensed form. Okay? So we have 1, 2, 3, 4, 5, 6 carbons. And let me rewrite that. That's kind of messy. Okay, so we have 1, 2, 3, 4, 5, 6 carbons. So this would be a CH3, CH2, carbon, triply bonded to carbon, CH2, CH3. All right, so this represents that, this represents that, this represents that carbon, that represents that carbon, that represents that CH2, that represents that CH3. Okay, so this is right here our condensed formula. Okay, now if we write the expanded Lewis structure, so we have again 1, 2, 3, 4, 5, 6. We have 6 carbons. So between carbon 3 and 4 goes your triple bond. And we just backfill with 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Backfill with hydrogens. So no hydrogens go on this carbon because it has 4 bonds. None go on that carbon. And H, 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 H. Okay? And this represents that, this represents that, this represents that, that represents that, that represents that, and that represents that. Okay? Now, if we try another example that involves a double bond. So if I draw something like this, 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 let's just put a BR right there. Okay. How would we draw our condensed structure? Well, we need to count the number of carbons. 1, 2, let's say we have 1, 2, 3, 4, 5, 6. Let's just arbitrarily number it like that. So we have carbon, and this is doubly bonded to a carbon with 2 hydrogens. So this would be 1 right here, and this would be 2. We have to remember what we have implied hydrogens. So that would be what? CH. This would be C. This would be triply bonded to another C. That would be bonded here to a C. We have to remember what this is in what H. So we have CH, Br, and CH3. Okay. So that's our condensed. So this would represent this. This CH would be represented by that. That carbon would be represented by that. That carbon would be represented by that. This CH would be represented by this. And this is your Br and CH3. So I want you to draw out the expanded Lewis structure. Okay. And also on this one, I want you to draw the condensed and expanded Lewis structure. Okay. And for all examples, give the molecular formula. So you're pretty much up to speed on all of this. This is stuff that we did in chapter 1. This is stuff that you were already tested on, and you should already be familiar with it. Okay. Now, everyone should know what I mean by molecular formula. Okay. So I'll do this one for instance. We want to add up all the atoms that we have. So I have 1 carbon, 2 carbons, 1, 2, 3, 4, 5. I have 6 carbons, so that's C6. And I have 6 hydrogens, so C6H6. I helped you out right there. by doing a difficult one, and you can do the rest of them. Okay, so another topic that we covered last chapter. I'm slowing down a bit. I had a comment that said I talked a bit too fast, so I'm slowing down just a bit for everyone to absorb what I'm saying. Okay, so as you already know from last chapter, degree of unsaturation. And I abbreviated that DOU. Okay, so let me draw out another alkyne like this. Is it going to be the same one? And what I was saying was you could make your line all the way in. It doesn't matter. It means the same thing, that a carbon is there. And make that a double bond. And let me add one more group right there. So let's go ahead and, from memory, let's count out what we have. So for every pi bond, that counts as a degree of unsaturation. So I have one pi bond here, another pi bond here, that's 2, that's 3, another pi bond here, 4, 5. So I should have a degree of unsaturation of 5 for this molecule. Okay? So we remember that the ring counts also as 1 degree of unsaturation. Okay? Now we can do a long-handed version and calculate it. So this is a what? CH3. This is a CH3. This is a what? CH. This is carbon, carbon, carbon. This is carbon with what? 2 hydrogens. This is a CH2. This is carbon, carbon, and this terminal line here is a CH3. Okay, so let's count out how many carbons we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, this is supposed to be a H. That's supposed to be an H. All right. Now, let's count out. We have 10 carbons, so that would be C10. And let's count our hydrogen. So we have 3, 6, 7, 8, 3, 6, 7, 8, 9, 10. 11, and 12. Okay, so that would be H12. So this is the molecular formula. Now we can apply the degree of unsaturation formula to this and see if we get 5. And that formula was 2 times the number of carbons plus 2 plus the number of nitrogens minus hydrogens minus halogens, and all of that was divided by 2. So we don't have any nitrogen or any halogens. All we have is carbon and hydrogen. So we have 2 times 10 plus 2 minus 12. All of that is going to be divided by 2. Okay? Now, so that's 22 minus 12 gives us what? 10 divided by 2, and that's 5. So we get the same number doing it that way. Okay? So you have to recall what we did in chapter 8. Okay, so that's those procedures still apply. All right, now we're going to go in reverse. Okay, we're going to go in reverse. We're going to be given a molecular formula. Okay, draw the structure of an alkyne. So that is also possible. If we're given the molecular structure, we can draw if we're given the molecular formula, we can draw the structure of an alkyne. So let's take this formula, for example, a very simplistic formula, C6H10. Okay, now if we're given this formula, one quick easy way to do things is say, okay, for a fully saturated alkane, how many hydrogen should you have So we can look at that, and for a fully saturated alkane, we should have 2 times 6 plus 2. So we should have 14 hydrogen. Okay, so now when we take that number 14 that we should have and subtract it by the number we have and divide that by 2, that gives us the degree of unsaturation. So that's 4 divided by 2, which gives us 2. We should have 2 degrees of unsaturation. So one thing you can do is just draw out 6 straight carbons. 1, 2, 3, 4, 5, 6. Okay? Now, if we know we're going to have 2 degrees of unsaturation, that is going to be an alkyne because that's 2 double bonds. So, let's say I put 2 double bonds here. Okay? And I'm going to backfill with hydrogens. Okay? Now, let's count how many hydrogens we have. We have 3 here. We have 2, 2, and 3. So that gives us 3. That's 5, 7, and 10. That gives us the correct number of hydrogens. So we know we have the H10 portion correct. And we have 1, 2, 3, 4, 5, 6 carbons. So we have C6H10. And this is our alkyne for this formula. Okay? Now, of course, there are numerous geometrical isomers. Tell me if this is correct. Now, remember, I'm going to use example. Remember that these 3 lines mean carbon triply bonded to carbon and hydrogens. So here you have implied hydrogens. That's different from if we have a terminating line. Here, these are CH3s. Okay? Now, what we want to do is we want to check this structure. And see if this alkyne that I drew over here, if it has the C6H10 formula. Okay? Does it have that C6H10? Okay, well, this is a what? CH3. This is a what? CH3. This is a what? CH3. This is a C. This is a C. And out here is an H. Very good. So we have 1, 2, 3, 4, 5. And 6. 1, 2, 3, 4, 5, and 6. Okay. So we do have the C6. Now, I have to work these out the same way you do. Let's count the hydrogens. We have 3. We have 6. We have 9. And we have 10. So we do have H10. So this is a another isomer of an alkyne. So this is an alkyne with this same formula. Okay? Now, what I want you to do is draw two alkynes or two alkyne structures. For the formula, C7H8. Okay? Draw those two alkyne structures. All right. Now, going a little bit slower. Let's talk about bond lengths and bond strengths for alkynes. Bond lengths bond lengths. And bond strengths of alkenes. Okay, so the same thing still applies. We said that a triple bond is shorter than a double bond, which is shorter than a single bond. Okay? Now, if we put in order of decreasing bond lengths, and sp3, and this is relative for carbon bonds, and sp3 carbon-carbon bond is going to be longer than an sp2, which is going to be longer than an sp. Okay? Now, this is all relative to the S character that is present in the type of hybridized molecular orbital that that carbon possesses. And again, this is a review of what we did in chapter 1. All right. Now, let's look at the S character. S character. So you remember that sp3 had what? A fourth S character. sp2 had a third, and sp had a half. Okay? Now, since sp has the most s character, it will have the shortest bond length and largest bond strength. And I mean by bond strength, it is harder to break a carbon-carbon triple bond than it would be to break a carbon-carbon single bond. Okay? Now, all of this is true because the portion of the sp in the molecular hybrid, the s portion holds the electrons closer to the nucleus, thus giving it the shorter bond and the greatest bond strength. All right. Now, all of this is, like I said again, it's a review. And one thing about this book, it is somewhat redundant. Things that you have learned, it will introduce them again in a new chapter. So you learn about all your functional groups in chapter 1, and as the author goes through the specifics of each functional group's reactions and its properties, you will learn some things over again, or it will restate certain things over again. Okay? Now, these are all properties of this should be alkynes, excuse me, ALK. Of alkynes, not alkenes, alkynes. So this is C, triple bond C. Okay? Now, let's talk about the thermodynamic properties. The thermodynamic properties. Now, alkynes are very high in energy. If an alkyne undergoes a combustion reaction, it will release a lot of heat to the surroundings. So if we take, and we haven't named yet, but a common name, if we take acetylene, which is C2H2. I'm going to write same as carbon, carbon bonded to H. Okay. Now, if we take that molecule and it undergoes a combustion reaction, we can actually calculate the heat of the reaction. Exactly how much heat was released during the reaction. So a lot of you did this in 142. Okay. So let's take the reaction C2H2. And we're going to react that with oxygen. And it's going to produce carbon dioxide. And what else does your combustion reaction produce? It produces water. Okay? So, what I would like you to do is I would like you to balance the chemical equation and calculate the delta H of the reaction. Okay? So, in order to do that, you need the delta HF of this. You remember that a diatomic gas, delta HF was 0. And you need the delta HF for this and the delta HF for that. Now, if you do not balance the equation, your calculation will be incorrect. Now, just as a refresher, I will do an example. Using a different molecule. So, I'm going to do an example, and this example will allow you to complete this example. So I'm going to just say CH3 plus O2, and that's going to produce carbon dioxide and water. This is called combustion reactions. All right, you did this in 142 and 141. Okay, so to balance this, I would have 5/2 of that. I'll have 2 of those. And let me see, 6 hydrogens and a 3 there. All right. That would balance it. That's 4 oxygens, 5 halves times 2. That's 5 right there. 6 and 2 carbons. Okay, so that's completely balanced. Now, the information I need to calculate delta H of the reaction. I want to know how much heat this combustion reaction produces. So I need the delta HF of H2O, and that's going to be negative 241.6 kilojoules per mole. Okay. I need the delta HF of CO2, and that's going to be negative 393.5 kilojoules per mole. And I need the delta HF of CH3CH3. And that's going to equal 226.7 kilojoules per mole. I think that's the right number, 227. Okay. Now, so delta H of the reaction is equal to the what? Sum the moles of the product minus the sum of the number of moles of reactant. Okay, so what we want to do is we want to take the reactants. We have 2 CO2s. We want to take that value of a negative 393.5 kilojoules per mole. I want to add that 3 moles for the heat of formation of water minus 241.6 kilojoules per mole. Okay, I want to bracket that. Okay, and then I'm going to subtract off the delta HF of O2, diatomic gas, is 0. So I'll just be subtracting off the 226.7 kilojoules per mole. Okay. So when you add all of this up, you go through and do the multiplication and add it up. This is only 1 mole of water. So when you go through and you do all the multiplication, addition, and subtraction, you get a negative 1255.3 kilojoules per mole, and that is equal to delta H of the reaction. So you see how much energy is released when you do the delta H of the reaction. This is exothermic. Now, you also can, if you know, let's say, if you know the delta H of the reaction and you know the heat of formation of CO2 and the heat of formation of H2O, you could actually go back and calculate the heat of formation of CH3CH3. Okay, but this is something I want you to be aware of, how much heat that can be generated from a combustion reaction of an alkyne. All right, so work that problem. I did an example that you can go by, and you can refer to your general chemistry book if you have any problems. Okay, now the next thing we want to talk about is the acid properties of alkynes. Okay, the acid properties. So it's actually acid properties and hybrid relationship. Okay, so the more S character that a carbon attached to, the more S character that the carbon that's attached to a hydrogen has, the more acidic it's going to be. That's one way to phrase it. Okay, so as you can see, the S character goes up as you go down. So your acid so what I mean by that is a hydrogen. If I go ahead and just make that a hydrogen, and I make this a hydrogen, this is sp hybridized. This is sp3. Now, since that carbon in this alkyne, this has a special name, that anion, I'll talk about that. But since this is sp hybridized, it has more S character. This carbon has more S character where this hydrogen is attached than this carbon with this hydrogen attached. So this is going to be more acidic. So a alkyne hydrogen would be more acidic than a hydrogen attached to an alkane. Now we need to keep in mind, or I need to introduce, two types. We need to know about two types of structures for alkynes related to acidity. Two types of alkynes. Okay, we have one we call terminal. Okay, now a terminal alkyne is where one of the sp hybridized carbons is attached to a hydrogen, and we can think about that as the endpoint. Okay, so what I mean by that is, let's look at some examples. This is a terminal alkyne. Okay, one of the sp hybridized carbons is attached to a hydrogen. That would be a terminal alkyne. Okay, let's look at another terminal alkyne. That is considered to be a terminal alkyne. Okay, let's look at another one. That's a terminal alkyne. That is a terminal alkyne. It's terminal alkyne in the sense that all of these have an H, H, H. Okay? Now, the second type of alkynes is internal. So, an internal alkyne both, and I'm just using a generality so you can understand. I'm not going to go into detail about any other atoms, but both sp hybridized atoms are bonded to other carbons. Okay, so this has a very important relationship to acidity. This has a very important relationship to acidity. So, if we can differentiate between an internal and terminal alkyne, so let's look at some internal alkynes. This is internal. Okay, why is this internal? We have a carbon, and this carbon is bonded to another carbon. This is a CH3. This is a CH3. That is an internal alkyne. All right. This is an internal alkyne. Okay. You see the difference in this one, which is a terminal, is bonded to an H. But on both sides of these sp2 carbons, we have another carbon that it's bonded to that makes it internal. Okay, let's look at another example. This is considered to be an internal alkyne. This is an internal alkyne. This carbon, 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 carbon. This carbon has 1, 2, 3, 4 bonds. This carbon has 1, 2, 3, 4 bonds. And they are attached to other carbons. So all of these are considered internal alkynes. Okay, now why is that important and what does it have to do with acidity? Terminal alkynes are very acidic. Okay. Terminal alkynes are very acidic. It is very easy to remove. Let's look at this example. Okay. So if I draw that, this is the same as that's the same as that. So that terminal alkyne means the hydrogen of a terminal can be it can be deprotonated, which means the hydrogen or the H plus can be removed. Okay, so if that H plus is removed, then we're removing the hydrogen proton, not the electrons that go along with the hydrogen. We're only moving the hydrogen protons. So what I mean by that is, let's take this same example. So if I deprotonate this with some very strong base, what we would have left is 2 electrons on that carbon, and that would give it a minus charge. If you calculated your formal charge, you would have 4 minus 1, 2, 3, 4, 5. That gives you the minus 1 charge. So I'll write this again. Same as this here. Carbon triply bonded to carbon. Those two are the same structures. Okay? Now, how do we deprotonate a terminal alkyne? So, let's look at the next topic of using bases to do such. Now, this has a general name. It's an alkynide ion, A-L-K-Y-N-I-D-E ion. So what we want to do is we want to make these alkynide ions. When we make these alkynide ions, we can use them as nucleophiles. We can use them as nucleophiles to make longer carbon-carbon bonds. It will be a carbon-carbon triple bond, but then we could use some agent to add a functional group or reduce it down to an alkene or an alkane. But the most important part is we want to increase the carbon-carbon chain. Okay? So, making an alkynide ion, and that alkynide ion is going to be RC triple bond C minus. Okay, it's going to take that form using NaNH2, that's sodium amide. Okay, so we can use NaNH2 to make the sodium amide. The alkoxide ion or hydroxide cannot do it. NaNH2 will make the alkynide ion. Now, several textbooks write sodium amide different ways. Sodium amide can be written as this. It could be written as Na plus NH2. You have 3 lone pairs on that nitrogen, give it the minus charge. Sometimes it's written as Na plus and just simply NH2 minus, or it can be written in this ionic form, NaNH2. You need to remember all of these are the same. Okay? Now, anytime we react a terminal alkyne with sodium amide, we get an alkynide ion. So let's take this for example. Okay, so if I react that with NaNH2, that's going to give me this, and I would have a minus charge. So keep in mind that this was an H. Okay, this is CH3, carbon, carbon. This is the CH3, carbon, carbon. So I just deprotonated the hydrogen. Okay, so actually these two electrons go with that carbon, and that's why we have the formal charge of -1. And hydrogen has a plus charge. Okay, what if I used that alkyne plus NaNH2? That would give me minus charge. Okay, now this is the same as carbon, carbon, like that. Okay, so you have to be able to recognize the implicit, be able to recognize the carbons and those implicit hydrogens, because this is actually a hydrogen right there. That gives it the 4 bonds. Okay, now as I said, what we want to do is we want to use the alkali ion as a nucleophile to make long carbon carbon chains. Okay, now the last part that we'll talk about is naming alkanes. Excuse me, naming alkynes. Naming. I already have something. Let's see. Aha, here we go. Naming alkynes. All right. So, as in anything, priority of functional groups determine the procedure for naming. Okay, so you remember when we had a alcohol and it was on a carbon-carbon chain and the alcohol took priority? Well, we need to learn about these functional groups, and because we're going to have more than one functional group on a carbon-carbon chain, and some of those functional groups do take priority over another. Okay, so there is a sequence. What I'm going to list is not all of them, but there is a sequence of prioritizing functional groups. So if we had, and I'm going to write this in decreasing order of priority. Okay, so if we had a C double bond O, which is a carbonyl group, that would take priority over an alcohol. So when we get to naming ketones, you will see what I mean by that. And your alcohol takes priority over the amine, and the amine takes priority over the alkene, and the alkene takes priority over the alkyne. This is alcohol, alkene, and alkyne. All right, so we haven't talked about exactly how to name them, but you have an idea with the word "ine." Okay, so a straight chain of carbons would have alkane. Okay, that's just carbon single bonds. Now, when we get to a triple bond, we have to get rid of the A and go to Y, ALKYNE. This is for triple bonds. Okay, so for example, let's say we have all right, the procedure is the same. You need to count your longest carbon-carbon chain. So I have 1, 2, 3, 4, 5, 6. All right, so I want to get to the triple bond first. Since that's all I have on this, I want to get to the triple bond first. So it starts at carbon 2. So that is 2 hexyne, or hex 2 hex 2 ine. All right, now do another example. Just and notice you have to get the geometry right. Notice that each carbon that's attached to the triple bond is linear. If I did this, that would be wrong. That is incorrect. Your sp hybridized molecular orbitals What forms a bond with those must be linear. Okay? Now, this is going to be, and let me put a functional group there. All right. Not a functional group, but an halogen. All right, so I want to get to the triple bond first. 1, 2, 3, 4, 5, 6. So it's going to be 4 bromo dash 2 hexyne. That's 6 carbons again. 1, 2, 3, 4, 5, 6. Or 4 bromo hex 2 YNE. Okay. Now, if I have a terminal alkyne, let's say we have 1, 2, 3, 4, 5, 6, 7 carbons. So I can call it regular hex, hept. Heptyne, I can call it 1 hept. But it's understood since the triple bond is on carbon 1, or I can call it hept 1 YNE. All of those names are the same. Okay? Now, when we put other functional groups on the carbon-carbon chain that have priority over the triple bond, we have to do a little different format, okay? That's why it's always good to know your priority, your sequence of priorities, okay? Now, let's say we have a double bond with the triple bond. I'm going to say this, 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 and let me put a halogen in there somewhere. Okay. Now, since we have multiple bonds in the chain, and what I mean by multiple bonds, I mean we have a double bond and a triple bond. We need to get the longest carbon chain that includes the double and triple bond. So if I count this way, let's see what this gives me. 1, 2, 3, 4, 5, 6, 7, 8. That gives me 8 carbons. Now, the double bond, it takes priority over the triple bond. So the double bond must have the lowest number. Okay? Now, when we have a alkene, the double bond, and a triple bond in the same molecule, we have to the last name in some cases is normally the one that has priority, but not in this case. The YNE will go last even though the ENE takes priority. Okay? So, what I mean by that, let's try this. On carbon 1, we have a ene that represents a double bond. On carbon 3, we have an ine that represents a triple bond. Okay? On carbon 5, we have a Br, and on carbon 6, we have a methyl. So what we have to do is we have to put all of this together. We want the double bond to have the lowest number, but it's going to come before the last name Y and E. Okay, so we have 8 carbons, so that's going to be an oct. Okay, now the ENE is going to go first. So I have 1 ENE. Now, since something comes after that, just like in the enols, I have to drop the E because I have the ine that's going to come after that. So that's going to be 3 YNE. Okay? So the YNE comes last when we have when we have a triple and a double bond. And on carbon 5, I have bromo, so 5 bromo. And on carbon 6, I have 6 methyl. Okay. All right. Now, we could write this as, let's say 5 bromo, 6 methyl, 1 octene. I would have to drop that E again, and that would be 3 YNE. Okay. Let's try another example that includes the So I'm going to just move the bromo around and I'm going to put the double bond there. Okay, so let's number what we have. 1, 2, 3, 4, 5, 6. 6 carbons again. And what do we have? We have the ENE on carbon 1. We have the YNE on carbon 3. And on carbon 6, we have a bromo. Okay, our longest chain is 6 carbons. So we're going to have 6 carbons is a hex. And I can write 1 EN. Remember, I have to drop the E because something comes after that, and it's going to be 3 YNE. And 6 bromo. Okay. Now, let's talk about a case where we have more than one triple bond, a diene. Just like a diene was 2 double bonds in the molecule. Let's talk about a diene and triene and so forth. More than one triple bond. Okay. So if I draw a structure like this and this, okay, we want to go through both carbon triple bonds. That gives us the longest chain. So 1, 2, 3, 4, 5, and I'll just use that one as 6. Okay, so we have a ine on carbon 1 and carbon 3, and we have this group that's not in the longest chain. Let me circle your longest chain in yellow. This is your parent chain here. Okay, so we have a methyl on 5. So we have 6 carbons, so we're going to make that and this should have been all right. This is going to be 5-methyl. We have 6 carbons. Now, the 6 carbon chain that contains the 2 triple bonds. Those 2 triple bonds we have to call a diene, a diene. This is 2 triple bonds. Okay, so we have to write 5-methyl, and I can write hex. I have to write hex to indicate the multiple triple bonds. 1,3 dash di YNE. Okay, or 5-methyl dash 1,3 dash hexa diene. Okay. Now, I was going to work this one in the video, but I think this is a good problem for you. Name this structure and notice that is a double bond, not a triple bond there. All right, that's another one of your quiz problems to grade. All right. Now, what about the case of an alcohol with the triple bond? OH and a triple bond. So we know that the OH molecule takes priority over the triple bond. Okay, so I can say OH has a higher priority than the alkyne. Now, if I draw out this structure, and I'm just going to put a OH there. Okay, now let's look at what we have. I'm going to circle the longest chain, so I want the alcohol to come first. Number first or have the lowest number. So going in this direction would give me 3, 4, 5, 6, 7. That would give me the alcohol to have the lowest number. It would be 2 going in that direction. The other direction would be 1, 2, 3, 4, 5, 6. Okay. Now, so on 2, we have OH. All right. On 4, we have a YNE. Okay. And we have what? 7 carbons total. So we can say hept And in this case, since we don't have, since the triple bond and a double bond are not present, we have a triple bond and a alcohol. The OL is going to come last. Remember that the OL is going to come last in this situation. It's going to have priority and it's going to come last at the end of the name. So we have helped, and on 4 we have a Y and E. Everybody agree with that? Now, since something comes after the Y and E, we have to get rid of the E, just like in the E and E. And then we're going to put 2 OL. Okay. Now, I could rewrite this as, let me see, could I write 4 help TYN E, 4 help time. Okay, I have to delete that E, and then I could write 2 OL. I could write that. That would be a sufficient way of writing it. Now, I'm going to draw this molecule again to illustrate something. And what I'm illustrating is you have to retain what was learned in the earlier chapters in order to be able to answer questions. In future chapters. This has, make that a H and a OH. This has stereochemistry. This is a chiral center, okay? And let's prioritize. So this would be 1, this would be 2, that would be 3. So it's going in that direction, and my lowest substituent is projected away, so that would be the S conformation. So if I gave you that dash and wedge, this actually would be S. Help. Four dash Y N 2 O L. Okay. It would have the S absolute configuration. All right. Can you draw the Newman projection of this molecule along the 2,3 carbon axis? You put an eyeball right there. So of course you would have a H coming towards you and an H going away. Could you draw that Newman projection? So this would be what? This would be a CH3 pointed up, coming over to my right would be OH. I would have a H. On my back carbon going up would be a hydrogen. To my right, to my left would be another hydrogen. And coming down, what is all this stuff that's coming down? This is a C. This is another C. This is a CH2 right here. And this is a CH3. That would be the Newman projection of that molecule. Okay? Now, can you draw the Fisher projection? You never really get away from all of this stuff. So, the Fisher projection, if I looked at it head on, I would have OH going down, H at the top, CH3 over here, and then this would be this CH2, C, CH2, CH3. That would be all of this. All of that. Okay. Now, do I have the same S configuration? I don't know. Let me see. 1, 2, 3. That's going counterclockwise, and H is on the what? Vertical. So that is S. That matches this. Okay. Now, the last one we'll do is naming a molecule with a double bond, a triple bond, and an alcohol. So we will have a double bond, triple bond, and alcohol. All right. So if I have a structure such as this, and I'm just putting some halogens in there to keep you refreshed. Now, what I want to do is I want to include the I want to include the longest carbon-carbon chain with the alkyne and with the alkene. Okay, so also with the alcohol, because this is going to be the parent chain. Okay, so your OH takes priority over what? The double bond, and that takes priority over the triple bond. So this would have the lowest number. Okay, so let's name 1, 2, 3, 4, 5, 6, 7. All right, that would be the correct direction for numbering. So on carbon 2, we have a what? OL. On carbon 3, we have a YNE. On carbon 5, we have a bromo. On carbon 6, we have a chloro. And also on carbon 6, we have a ENE to represent the double bond. Okay, so when I put this all together, we have a 7 carbon chain. We're going to have hept. Okay, now the ENE goes before the YNE, so that's going to be 6 ENE. Remember to drop the E because something comes after that. And what's going to follow that is the yne, 3 YNE. Remember to drop the E on the yne because something's going to follow that. And what's following that is the 2OL. All right. So we have 5 bromo dash 6 chloro hep 6 ene 3 yne 2 OL. All right. Now, the only other way I could think of naming this would be 5 bromo dash 6 dash 6. Remember to drop that E. Three YN 2 OL. Now, a lot of students, they resisted the the procedure to use the numbering system at the end. Some students like to call this 1, 2, 3, 4, 5, 2. Some students were fixated on this method and this method alone. And I told students that you need to really get familiar with the numbering coming at the end of the name. This is the reason you needed to learn the numbering at the end of the name, because not all the time when we have molecules that have more than one functional group, this would be the only way to name it. All right. Now, in addition to those that I've told you to work, I want you to name the following for these. Write the molecular formula and draw the line angle structure. Okay. On this one, I want you to name the following and write the condensed structure and write the molecular formula. Okay, so each quiz problem will be worth 0.2 points each. Okay. On next time, we will pick up on reactions of alkynes. The reactions of alkynes are very similar to the reactions of alkenes. So those who did well with the alkene reactions, you will do very well with the alkynes. There's just one more bond that the electrophile adds to, and we can keep reducing down in some instances.